We move on to another force, which is the tension force. We are all familiar with this force. This is just one example. We use a rope or a string to pull things. There will be a force in this string. We call it a tension force. So here in the rope, there is a force exerted by the man, tension force going this way, and this is the reaction force. You remember Newton's third law, action, reaction, pair of forces. Here, the tension on the car, okay, and as a result, the car now is moving. So the function of the rope or string is just to transmit the force, okay? But it's helpful, it's convenient to use strings in mechanics and ropes. Another example for tension force. Here we have a static object. A static object means acceleration is zero. There is no motion, so the acceleration is zero. So if you write the equation for the object in Newton's second law, the net force is T minus mg. Net force equals MAY. AY is zero because there is no motion. So T minus mg equals zero, or T equals G. So the tension force in this rope is equal to mg, the weight mg. If there is acceleration involved, then we have to take the acceleration into consideration. So here, think of this situation: a mass hanging in an elevator. The elevator is moving up with acceleration A. So now the net force is equal to mass by acceleration. This is Newton's second law. And the net force is T minus mg. T minus mg. Okay? So now when you solve, you get T equals m multiplied by AY plus G. So now the tension is greater than mg. Another situation, we have symmetric angles. The object is hanging with these two ropes here. So now to solve for the tension, decompose T to vertical and horizontal components. The vertical component is T cosine theta, and the horizontal is T sine theta. Do the same for the other tension. T sine theta horizontally will cancel with T sine theta horizontally. We end up with only the vertical components, T cosine theta plus T cosine theta. Since there is no motion, so acceleration along y is zero. Therefore, 2T cosine theta equals mg. Okay? No motion along y. 2T cosine theta minus mg equals 0. Therefore, 2T cosine theta equals mg, or T equals mg divided by 2 cosine theta. Another situation, two tensions at non-equal angles. Non-equal angles. Again, we decompose T2 into horizontal and vertical components. The horizontal component will balance T1, and the vertical component will balance mg. Okay, so in this case, T2 is mg divided by cosine theta. For the horizontal, there is no motion. This is static equilibrium. So 0 equals T1 minus T1 plus T2 sine theta. So from here, we can solve T1 in terms of T2. T2 also. We know T2 is the first part, so we can solve for T1. It is mg over cosine theta multiplied by sine theta. Sine divided by cosine is tangent, tan theta. If you have a rope like this with two tension forces, they must be equal. If they are not equal, the rope will break. This is assuming it has no mass. Mass is 0. So if m is 0, then T must equal T prime. Always when you solve problems using a Newton's law, you sketch the forces. We call this the free body diagram. You check all the forces, and then you start applying Newton's laws of motion. Okay, so here you have the gravitational force downward, mg, the normal force upward, and the tension in the rope horizontally going this way. Assuming no friction, assuming this is to be smooth surface, frictionless surface, then T equals max, and for the vertical direction there is no motion, so may is 0. It's equal to n minus mg, so therefore n equals mg. From the first equation here, ax is equal to T divided by m. Always when you solve problems using Newton's laws of motions, it's always good to read the problem twice at least, make sure you understand it. Then draw the free body diagram, the picture, identify the force vectors, label the picture properly, and then apply Newton's second law and solve for the unknown. If the system is in equilibrium, this means the net force is 0. If the system is in equilibrium, the net force is 0. When we say the net force is 0, this means net force along x is 0, net force along y is also 0. If there is 3 dimensions, net force along z is also 0. Consider the two situations here. There is no acceleration. In both situations, there is no acceleration. In both cases, the men pull with a force of magnitude F, so the magnitude of the force is the same. How does the reading on the scale in figure 1 relate to the reading on the scale in figure 2? Any suggestion? Since the force is the same, then the reading of the scale will be the same, right? So the second man here serves as the wall, just to hold the scale, but it will not make a difference for the reading of the scale. For the woman being pulled forward on the toboggan in the figure below, the magnitude of the normal force exerted by the ground on the toboggan is? Any suggestion? Okay, less than the total weight, because the action of the force this way will make the normal force less, and the normal force less, okay, makes friction less, and this way the magnitude of normal force by the ground will be less than the total weight.